Sure.
People have like some separation of time scales between thermalization and scrambling. What kind of definition do you need for scrambling in that sense?
So, right. So I guess often, right? Often it is defined in terms of autok, and to get yeah, I guess generally, so you need some large n theory for that. But yeah, let me maybe come back to it. Yeah, that's a good question. So any other questions? Yeah. Okay. So that's then let's go to many body localization. Right, and let us start. Let me start right away with the model, and I'll just model that I will start from would be what we already had yesterday. So it's spinless fermions on a lattice, and let me stay in one dimension even for now, for simplicity. Plus interaction. Where EI is random and drawn from some distribution with typical width W. And so, and first of all, the starting point is that if I forget about interactions for a moment and just look at first two terms, right, what I have is particle. It's a non-interacting system, right? I have a particle hopping on a lattice where on-site energies are random, right? And hopping is nearest neighbor. So in such a system, you have a phenomenon of Anderson localization. And so, is it something that most of you have seen somewhere, Anderson localization? Yeah. Okay, so idea is that, because of this mismatch, energy mismatch between nearby levels, right? If your hopping becomes smaller than the typical mismatch, so in the regime where T is smaller or much smaller, right, than W, typically nearby sites would be off resonance, right? So you can do usual perturbation theory and not degenerate perturbation theory. And then your wave functions, right? Your wave functions actually can be constructed generally perturbatively. So I can introduce an operator Ci dagger, which would create a localized state centered around I, right? And it would have a certain, it would decay exponentially, right, with a typical scale, which is Xi0, which is localization length. Right, and it's a single particle localization length. Now, we would be mostly interested in this regime of strong localization. And strong here, yeah, refers to the fact that simply typically you don't hybridize with your neighbors, and non-trivial part of it is that even at higher orders, you would not hybridize with sites which happen to have energy which is close to your energy, right? Because to get there, you have to go through many off-resonant processes. It would be a high-order process and perturbation theory, right? And matrix element would decay exponentially, while closest energy you would find some distance x away would only go down polynomially for single particle system. Of course, right, of course, there is also, in low dimensions, there is also a phenomenon of weak localization, which tells you that actually in this model in 1 dimension and 2 dimensions, for arbitrarily weak disorder, even when this is not satisfied, all the states would be localized eventually, right? And that's comes, I mean, there is also a very nice theory, right, of weak localization having to do with, essentially, in that case, you do expansion in 1 over your Fermi wave vector times mean free path, right, and build a theory of how interference corrections actually enhance probability to return, right, and eventually completely localize you. So that's an important piece of physics which we will not touch because we will be interested in the effect of interactions, right? And there turns out to have a for localization to be stable or long-lived, right, you have to be in this regime where t is smaller than w and localization length is relatively short, right? It's order 1. Right, so you're localized on just a few sites. Then, it is convenient. I can reformulate my model in terms of localized, single particle localized orbitals. So I have epsilon I, ci dagger ci, plus some, and then, interaction term would be a quartic term in C and C dagger with some matrix elements, KL, CI dagger, CJ dagger, CK, CL. So, and it would be non-zero when, I can take 2 particles, I and J within localization length, and then move them to some other nearby orbitals. And of course, for processes which involve particles very far away, this would be strongly suppressed. Similarly, sometimes we would find it more convenient to think about spins. Right, I can consider first the solvable limit of just non-interacting spins, right? Trivially solvable, and then I can add a general local interaction which allows spins to hybridize, right, and exchange energy and flip together. So, and this could be some local generic interaction. And in fact, this particular model you can map onto the spin model, right? Onto the spin model where interaction would be just XXZ type interaction, right? So it's a matter of convenience. Ultimately, the physics of the two classes of models would be similar. Now, notice I would require that my system is not very symmetric. So, for example, I would break any continuous non-abelian symmetry, right? I would not want to have SU2 symmetry, for example, for reasons that we can discuss later. And the difficulty. So, and then the question, right? The question we can pose, and it has been posed, for many decades. We can ask whether, upon turning interactions, so whether the system remains localized in some sense, right? And now, in terms of sort of why it has been, a very, very important problem, Anderson localization. Well, because it essentially, for example, if you're dealing with a disordered solid, right, and you Anderson localize, then you become insulating, so conductivity is 0. right? And you have this notion of Anderson insulator, which indeed, there are many experiments seeing localization in disordered semiconductors, for example, right? And phenomenon of Anderson localization also arises when you study propagation of waves in disordered media, right? So it's quite generic, right? It's not even just limited to quantum systems, right? But also applies to waves. So, and therefore a natural question to ask, well, we see Anderson insulators with zero conductivity. So what is the role of interactions? Because of course, in a solid we always have Coulomb interactions, right? So, and you can ask, so what is the role of interaction? Right. So, and in particular, does localization survive? Right. Do we stay insulating, or is there some very long time scale where things would move? And in particular, is the conductivity finite, or does it stay strictly zero? Right. So that's been, a question that people try to address in various ways, right? And it's a difficult question, partially because you are starting, if I think about many body states, right, and I try to use this logic of hopping and hybridization, right, I really have to find a way to take into account that my energy comes from a local functional, right? So I would not be, so I could try the following. So let me try something that will not quite work out, right? So let me consider this type of a model where I will choose interaction to be J sum sigma ix sigma I plus 1x sigma iy sigma I plus 1y plus sigma z. Right, so it becomes the random field Heisenberg model, and that's a model that's been studied a lot in the context of many-body localization. And I could try the following. I could say, well, let me take product state basis. Right, so I have, these are my basis vectors. I have 2 to the power n of them. And let me treat them as sides, right? Sides of some, in this case, they would form a hypercube. Right, so I can think about n-dimensional hypercube, and states would be vertices of this hypercube. And then I can say, well, there is a diagonal piece of energy here. So there is a diagonal part of sigma z, so which is just sum hi sigma iz. And then I can add the interaction here because it's diagonal, right? It's diagonal, so it just gives me on-site energy. And then this term would allow 2 neighboring spins to flip, right? So then I can choose any 2 neighboring spins and flip them, and that would move me, right? That would allow me to move along any diagonal on a face of this hypercube, right? Which share, I start with 4 vertices, I can hop across diagonal. Moves are local, right? But then I could say, well, there are n minus 1 neighbors, to which I can hop with amplitude j, right? And each such hop changes energy. Delta energy is, essentially it's hi. It would be something like sigma iz plus hj sigma jz, maybe with a factor of 2, right? And plus there would be a difference in the interaction energy. Well, in this case, actually, interaction energy would not change, I think, so it would be just this part. And then, so what you could argue, you could try to use this logic, well, am I finding lots of neighbors which have approximately the same energy as me, such that hopping is much greater than energy difference? Because if that happens, then I would argue, well, there is hybridization, right? And my system becomes delocalized, as we saw for thermalizing systems. Right, so you're hopping does this, so it flips. Sorry, I'm not being very good about notations here, so this should be, of course, hi plus 1 and sigma I plus 1. So it takes, for example, this configuration and flips it to this configuration, right, with amplitude j, which I should compare to change in energy, right, which is a random variable. But I could say, well, in fact, I have number of sort of connectivity of this hopping problem is, let me call it k, which is of order n over 2. N over 2 because I'm only allowed to flip up-down configuration, but not up-up or down-down. And therefore, I would always find lots of resonances, right? Lots of states to hybridize with, right? So naively, I would say there are many resonances. And for me, a resonance is when energy difference is smaller than the hopping, right? And then a priori, I have to do degenerate perturbation theory, and that leads to delocalization, right? So number of resonances, roughly, I can estimate it as the connectivity times j times over w, right? And that gives me something of order L j over w. Right, so lots of resonances. Of course, the probability is that two nearby spins are in resonance is j over w, but I have lots of pairs, and I can flip some of them, and they would get hybridized. And then if I take this at face value and say, well, on this hypercube, I'm always finding, I have lots of neighbors. I always find neighbors to hybridize with, right? This would lead to percolation of resonances, and you would say your system is always delocalized, right? But this is not, right? This is not actually reality, and what this argument ignores is locality, right? Because it tells me that, somehow it tells me that if I now think in terms of spins, sure, probabilistically I would find some resonances. For example, these two spins would be in resonance because hi minus hi plus 1 happen to be smaller than j. And then there would be another resonance far away where hj minus h plus 1 j happen to be smaller than j. right? And what I'm saying is that, well, if I take this logic, I would say that my wave function is somehow, there is some state of other spins, right? So let me say they stay in the product state, and then state of spins ij, I and j looks like that. So it's sum a I plus 1, j plus 1, sigma I plus 1, sigma j plus 1. Right, such that, this is an entangled state, and that's what this logic would suggest to me, that they all hybridize, and this ends up in entanglement between faraway resonances. But in reality, right, of course, this is not somehow physical, right? If I have a resonance here, but I have a big localized chunk between this resonance and other resonance, they cannot easily exchange energy, right? So they would not be actually in resonance. And the way to, right, intuitively, so instead, what you expect that your wave function would look something like that. So it will be, you have superposition of your spins, in the first resonance, which end up in a, in a degenerate perturbation theory, so they have to get entangled in the eigenstates. Then let's say in between, I have nearly product states with small corrections, local corrections, and then I have another resonance here. All right, so there is still no, this is my resonance 1, and this is a resonance 2. Right, so in fact, the system would stay localized, right, if matrix element connecting this resonance to that one is sufficiently suppressed compared to their, level spacing, right? And naturally, if nothing dramatic happens here, right, you expect that you can do perturbation theory, and this would be, the matrix element coupling, for example, these two states and these two states would be exponentially suppressed in the separation, right? So really, intuitively you expect that the key property of many body localized eigenstates, assuming for now that MBL is stable, is that they have little entanglement, right? MBL eigenstates right? So, and logic here is the following. So I start out with this model, for example, right? And I work in the regime, well, this model. So, and let me work in the regime where J is much smaller than W. Then in places where I did not encounter resonances, right, where, Hi minus Hi plus 1 happen to be, and typically it would be of order W, much greater than J, right? In most places, I would not encounter resonances. So then I can do usual perturbation theory, right? And my eigenstates here would be a product state plus small mixture of flipped configurations. Then, of course, there would be these resonances, so I'm guaranteed to find them. And then I have to make sure that they don't, they're rare enough, right, that they have hard time communicating and coupling through these localized regions, right? So that's a cartoonish picture of MBL phase. Right, so any questions? Yeah. So you're asking what is the typical entanglement of the states, right? Well, so first observation is that these are area law states, right? That these are area law states. So then, okay, question about entanglement spectrum is somehow another question. But if you, it is generally a power law. Right? It's decaying as a power law, but it's a it's a relatively fast decay. Are you asking to compare to? I mean, so typical MBL eigenstates can be thought of as ground states of some fictitious Hamiltonian, right? So they have. Let's maybe come back to it also, because that has to do with localization length, right? So, but generally, you can make a simple argument which will follow from a construction we will do next, and understanding sort of what local conserved quantities look like. Yeah. Mhm. Yes, right. So what I'm saying, right, is that, okay, so first of all, the counting of resonances, right? So that's clear, right? Or K is clear, right? And then the counting of resonances. So what I'm saying that for a given move, probability of resonance is J over W, right? And then I have K such moves, right? So okay, so number of resonances would be K times probability of a single resonance. So that would be the typical number of resonances, right? But oftentimes when you use this resonance logic, you are dealing with a situation where you're hopping on a lattice where on-site energies are independent, right? They're random. So let's say if you think about Anderson localization, right, you have random on-site energies which are not correlated in any way. But here, on-site energies come from this local functional, right? So they're very much correlated, right? They're very and that makes all the difference. So actually, rather than, so let's say if I said, okay, so that's my state, right? And I can make a move. I can flip spins I plus 1 like that, and j plus 1 like that, right? Then, so let's say here I'm starting from up I down I plus 1, up j down j plus 1. Then naive resonance logic would tell me, well, these three states plus the state with a double flip, right, where I'm flipping this one, and then also I would flip twice, right? They all would get hybridized and would start looking like a random wave function on these four sides. But that fails, right? Because we know that, right? We know that actually these resonances are living far away, right? So in fact, it looks like a product states of these two states and those two states, if it makes sense. Yeah. Uh-huh. Mm-hmm. Yeah. Right. Well, the what is missing in this logic, right? It would be absolutely correct if I had a hypercube where energies on vertices would have been independent variables, right? Random independent variables, right? But they're not, right? They come from this local So maybe, okay, let me, let me maybe consider even a simpler example, right? So let's say I have two spins, right? And the spins are J, well, not to introduce J, let me call it G, sigma 1x plus H1 sigma 1z, right? Plus J sigma 2x plus H2 sigma 2z, right? Then, of course, so these are non-interacting spins, right? So they would always be in the product state. Nevertheless, if I were to naively represent the four states as a hypercube, well, in this case, a square, right? I have up, up, down, up, down, 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 right? And then I have G, 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 right? And let me turn, right? Um, turn Z fields such that they're weaker than X fields, right? Then, uh, no, G, let me make G comparable to H, right? Such that naively I would say, well, they're actually in resonance, right? And then you would say, well, it's just a superposition, right? Superposition of these four states. But it's a very special superposition, right? Because in fact, I can diagonalize them separately, and I know they're strictly in the product state, right? And again, I think maybe it takes a minute to just to see, but really, the origin of that is in the fact that yeah, that's right, and that comes back to this, yeah. Exactly, right. It's a little bit, it's really the same picture, right? It's just now I have, resonances between up-down state here, down-up state here, right? And another resonance far away. But it's exactly the same, right? These are two spins which are in resonance, but they're decoupled.
I see. So, okay, fine. So what you're saying is like, when I imagine to apply my Hamiltonian time, for example, it's gonna entangle two neighboring states.
Mhm.
And in the next step of the Hamiltonian, imagine I do a discretization, I'm gonna also flip the other two.
The other spins there, right.
Say, okay, I gave this a superposition, this presence instead of this together.
Yeah, exactly, right. Right, exactly, right. Yeah. And you can see it, I think you can see it explicitly in various ways, right? Why exactly this form of energy implies that, this fails. But yeah, I think intuitively, right, this argument does it. Yeah. Okay, any other questions? And so, what I'm gonna do now, I'm gonna run with this intuition and then make an assumption, right? Make an assumption that this is what MBL eigenstates look like, right? And then explore the consequences, and then we would discuss how to justify it and where things are in terms of really, really determining where is the boundary of MBL phase and so on. Right, so if I take this picture of MBL eigenstates, I would say, well, actually, right, I can always start from product states. Right, start with product states, which are eigenstates of the, trivial part of my Hamiltonian, right, sigma z part. So let me call it H0, for example, right? So H0 eigenstates. And then if our intuition is correct, right, what I need to do to get eigenstates is essentially in the regions which are localized where I did not hit a resonance, create a little bit of entanglement, right, by admixing just a little bit of other configurations perturbatively, right? And then sometimes I would see resonances of 2 spins. More rarely, I would see resonances of 3 spins, right? And there I would have to make those blocks of spins entangled, right? But this entanglement would not spill over, right? It would not generate really long range, right? Long range correlations, right? And the intuition this suggests is that actually I can get an eigenstate, right? Eigenstate psi of my non-trivial many-body localized Hamiltonian by applying quasi-local unitary transformations. And quasi-local means that, so you can ask, right? You can ask what is quasi-local exactly, right? And I would give a few, a couple of intuitive properties. So for example, U acting on a product state gives you a state which is area law entangled, right? So it doesn't make very entangled states starting from product states. I can also, view U as a fictitious evolution operator. Right, and then it does not spread information. So for example, if I consider some local operator evolved with U, right? So, and let's say O is local, so it's maybe Pauli matrix somewhere, right? So let's say this is support of O. When I dress it and get O tilde, it would look like that. It would be a sum of, it would be picked here, right? And then it would have exponentially decaying tails far away. So it would not have sizable weight in products with lots of Pauli matrices far away. Right? So, and then, right, if we take this as a hypothesis for now, then we can diagonalize, right, diagonalize our MBL Hamiltonian by this quasi-local unitary. Right, and this is, right, this is the essence of what MBL eigenstates are like. Now, of course, probably burning question is how do you justify it, right? How do you do it technically? And so here I can outline the route which has been taken in one dimension, right? And you would see that there are some challenges which are quite non-trivial, right? But the way to substantiate it is as follows. So let me divide H into the diagonal part in the Z basis, and then J, and then I have the part which leads to dynamics, so which can and I'm going to treat this as a perturbation, right, V. And what I'm going to do is perturbation theory order by order in J over W, right, which I will do explicitly locally to keep track of this, of this fact that things, resonances far away should not get entangled immediately, right? And to do the first order perturbation theory, so, and I'll do it gradually, keeping track of locality, so I'll try to construct U kind of iteratively as a product of transformations, which would be less and less local and closer to unity. And in the first order, right, in the first step of this procedure, I would do a unitary which is explicitly quasi-local, right, or local even, right? I'm going to write it as an evolution with some fictitious Hamiltonian for some time, right? Where this Hamiltonian omega 1 would be of order J over W, and it would be explicitly local, right? So at the first step, my goal would be to find such U1 that this gives me something diagonal, right? First order diagonalized Hamiltonian plus other stuff, which would be of order J over W squared. Right? And this is a type of, what is sometimes called Schrieffer-Wulff transformation in the condensed matter literature. And here I'm going to say, well, let me look for omega 1 in the form where it's sum over omega 1 I. And this would be local terms acting on spin I and I plus 1. Right? So these things would be local. Local 2 or 3 spin terms. Now, strictly local, right? Really acting on neighboring spins. And then I'm going to use this assumption that omega 1 is small, right? So I can expand U1 to lowest order in omega, or maybe second order in omega. So I'm going to write e to the minus I omega 1 H0 plus V. Right, so I'll get, when I expand this, I'll get a commutator, right? So I'll get H0 minus I omega 1 H0 plus V, right? Plus I have other stuff, so I'll have, for example, commutator omega 1 with V, and I'll have double commutator omega H0, right? So, but let me focus on the term which is presumably of order J over W, this one, and choose omega such that this is 0. Right, and you can, so if there are no resonances, you would find that you can always solve this equation and find these local terms, right, that really give you the right admixture of, which do perturbation theory to order J in the right way. Right, so we have to solve the equation I omega H0 is V, and can solve, and omega 1 would be small over order J over W if there is no resonances. Then of course there would be resonances, and those I'll have to treat separately, and there you will have to become non-perturbative if you wish, right? That's exactly what we anticipated. Right, and this is the game you can play, right? So you can keep track of resonances and bound their probabilities and see that they're sufficiently rare. And then you can keep doing this, right? You do it to the first order, then you find the find the new Hamiltonian, which would be order J squared. And because you have now commutators, these operators would become less local, right? So you started out with 2 spin operators, now you might have 3 spin operators, right? And then you do it order by order, right? Each time, then I'll do it order J squared. Next next perturbation I would generate would be J to the 4th, right? So it goes like that. But you can see also that this becomes this rather tedious problem, right? Where you have to keep track of probability distributions, resonances, and so on. And to really prove MBL, you have to show it to an infinite order, right? You have to show that probability of having large resonances really doesn't explode and so on. And there is an attempt right now, already a few years old, by John Imbrie to really follow this through and then construct this quasi-local unitary that I mentioned. Right, okay, that's a difficult proof, so probably it can be simplified, and there are some maybe places which could be clarified, right? But that's one route you can try to take. And yeah, any questions? Time break. Ah, yeah, right. Yes, yes, yeah, good. Yeah, I think it's a good time for a small break, and yeah. But let's come back in, I don't know, 5-7 minutes maybe. Yeah. Yes. All right, so let's continue. And first, are there any questions about the logic? Yeah. Okay, so then let's explore, some implications, right? Because there is still, we formulated this idea that your many-body localized eigenstates can be obtained by quasi-local unitaries acting on product states, right? But that has also nice interpretation and nice implications, turns out. And we will come back a little bit to this, attempts to construct this unitary and dangers that you encounter a little bit later, probably tomorrow. So, but first here, let us discuss implications. Right, so sort of almost by definition, first implication is that MBL eigenstates generally have area law entanglement. And this is, of course, in a sharp contrast to what we saw for thermalizing systems, right, where excited eigenstates have volume law entanglement, which is identical to thermodynamic entropy. And this tells you that actually MBL eigenstates, from the complexity point of view, they are not very complicated. So in particular, right, you can approximate them to a good degree using matrix product states or tensor networks, right? Because those are the states really adapted for low entanglement. Second implication, which is also quite useful, is emergence of local integrals of motion. So I will loosely use term integrability, although you would see that it has very different origin and very different structure compared to the more familiar beta ansatz integrability, for example. Right, so, and to construct local integrals of motion, and here by local, I mean really that these integrals of motion would be quasi-local operators, right? They would have support centered somewhere and an exponential tails away from it. So let me call them Lioms, or also you would see that they're called either Lioms or L-bits. So eigenstate I can label eigenstate by set of choices for z projections of my spin. So let me call it psi alpha is u acting on a product state sigma jz alpha, right? So let me just number the configurations from 1 to 2 to the power n, and then you see that my MBL eigenstates are in one-to-one correspondence to the product states, right? And then I will define, right? I will define tau iz, which would be sigma z, which is deformed by our unitary, right? And of course, so tau z, you would find that eigenstates are operators, are eigenstates also of the tau z for every I, right? Because I can say, well, this is u iz u dagger, and psi alpha is u sigma jz alpha. Then this goes away because it's unitary. Sigma iz acting on this gives me a number, and then I get sigma iz, the number, times u sigma, right, times u sigma j z alpha. But this is, as we have here, this is the eigenstate, so this is sigma iz. Right, so this becomes a label, so tau z is is actually diagonal in the basis of eigenstates, so it must commute, right? It commutes with the Hamiltonian, and they also commute with each other. Right, so we got, right, this is implication that our system has a bunch of conserved quantities which are, I can view as pseudospins, right? So I have this conserved pseudospins. And the key here is that these operators are quasi-local, right? So they look like this, such that they're still, right, they still have overlap with physical observables, with relevant, right, physically relevant few body operators, right? Because, of course, the statement is very general, and I could have done formally the same for thermalizing systems, right? But there, this U would be horribly complicated, right, and very non-local and generating volume law entanglement. So there, this would become essentially projector onto some group of eigenstates, right, which in thermalizing systems is not, right, is not a physical operator. Right? Right. So in a thermal system, in a thermalizing system, tau iz can be defined, would be very non-local. Right, and this goes back to this idea that in any quantum system you have integrals of motion, but the question is how physical they are and whether they have bearing on physical observables. Right, so projectors onto eigenstates. So, okay, any questions about this part? Yeah. Mm-hmm. Yes, right. You mean with this part, with tau z operators, right? Yes, yes. Right. So let's think for example, the first approximation to tau z would be, okay, I forgot whether I was putting minus there or not, but let me say not. So then I have I omega 1 sigma iz e to the I omega 1, right? Where this is, you can think of this as an evolution for time for a short time j over w, right, with some Hamiltonian, some local Hamiltonian. So then this would not be, this operator would not spread very far in that short time, right? So I can write it as, I can say, well, there is some weight which is close to 1, 1 minus epsilon sigma iz. And then I can get some, two-spin operator, right? I'll have some small coefficient, epsilon 1 sigma iz sigma I plus 1 z, for example, right? Maybe I'll have epsilon 2 sigma x sigma I plus 1x, something like that, right? So, but the point is that this coefficient would quickly decay, right? And that's what I'm sketching here, right? That this operator is still, still local. So, for example, well, rather quasi-local. It's allowed to have tails, right? But these tails decay exponentially. Yes, right. Good question. So now imagine I would have tried to do it in a thermalizing system, right? And let's say the system is thermalizing from the beginning. So well, first thing I would find is that I have a, it's impossible for me to construct even omega 1, right? Because I have to deal with degenerate perturbation theory everywhere, right? Then I can still say, well, let me take a step back. Let's say I could have found eigenstates of my thermalizing system. I build this unitary, right, which takes a product state and gives me eigenstates of thermalizing system. But I know that, for example, if I were to represent it as e to the I some fictitious Hamiltonian G, right, G fictitious, it has to be a type of evolution which takes product states and turns them into, this very entangled thermal states, right? So it would have to be some evolution if it's local Hamiltonian or quasi-local. It would have to be evolution which runs for a very long time, right? Yes, exactly. So it's only, it's only has this property, and it only really is useful and relevant for many-body localized systems, to be more precise. Yeah, right. Because for integrals of motion to be really useful, they have to be local, quasi-local, right, or sums of local terms. And that's one such, right, one such case where where emergence of these integrals of motion is due to disorder, right? Thanks to disorder. Mhm. Mhm. How do I determine n? What determines n, you mean? Yeah, right. So it would be when so I would have to reach the size of the system, right? And then I stop. So essentially it would be, depending exactly on how I design my perturbation theory, right? But let's say at the, generally, if I arrived at some scale and my perturbation has range k, right? So I can act on, I have terms, which can flip a block of k spins in some way, right? That's the range of, right. So range of omega would be twice that, right? Because I can have a term, for example, which couples, right? Which couples right? Right, so that would be the range of omega, and then if I can perform that, I would reduce the strength of my coupling. It would become square of the coupling, right? So I half, right? I half it. So I would have to do some log, number of steps in the system size of this procedure.
As you said, like when I look at proceeding that way, I should really think as this omega 1 to omega n as being really strictly localized in space.
Yes, right. So there are sums of local terms which become less and less local. So at the last step, you would have omega n would be very non-local, right? But it would still be, by that point, you would have eliminated all the local potentially dangerous processes, right? And you have process just at the last step where you can flip all the spins, right? But with some incredibly small, something like that, right? Maybe there is a number there, but it would be amplitude for flipping all the spins together would be exponentially suppressed in the system size, right? And if our procedure succeeded, well, let me even call it, lambda to power L, right? And if that is much smaller than the level spacing, which is 2 to the power minus L, then we are in business, we can do this last step, right? And it would still stay, right? My last unitary would be close to unity, right? So, but that's how it goes indeed. So I make couplings weaker and weaker, but I have to deal with more and more processes, right? Eventually having to deal with, whatever 2 to the power L possible transitions. But actually, unfortunately, there is no way around it, right? And then that, going back to the comment I made that, they're area low, therefore they're simple. Well, the fact that they're area low does not help you, for example, to analyze this type of processes, perturbative processes, because simply this involves, right? There are lots of transitions, lots of processes, right? Sure, they come with very small amplitudes, but you don't have, your matrix product state does not give you enough sort of capability to keep track of all of them, right? So that's why, right, there are different notions of complexity, and truly proving that is hard, right? I mean, again, I don't think it's impossible, but yeah, we haven't beyond this paper of Imbri, so we did not really succeed yet. Okay, so that's right. That's the idea of integrals of motion, and then you can, in some way, you can view these tau operators as many-body, right? Many-body analogs of Anderson localized orbitals, right? Because I have in an Anderson localized system, right? I have my integrals of motion, I are just occupation numbers of a given, right? A given localized state. So here instead, so we, in a many-body system, we have to dress them, right? They acquire some many-body component, and then in the many-body localized context, so that they replace this type of single localized orbital occupations, right? So it's an extension, if you wish, generalization. And now, here, it's interesting to go back in history and, for a while, sort of driven by studies of disordered semiconductors, right? People were thinking about this issue of Anderson insulator with interactions, which of course is very interesting and important, right? But Anderson himself, right, he was motivated by a problem which is much more like what we are considering, like a spin system, energy diffusion, right? Diffusion in a spin system with disorder, rather than by thinking about right? Thinking about electrons in a electrons in a semiconductor, right? So he was apparently trying at the time to make sense of some experiments on spin um, spin dynamics that were done at Bell Labs, right? And actually, I mean, he makes a reference, but at least I couldn't find the paper about that experiment. And he clearly, clearly what he was after is solving the interacting problem, right? And understanding whether your system would thermalize and so on, right? But okay, so he could, right? He could simplify it and solve it for, for a single particle in a disordered, right? Disordered potential, right? Which is, I mean, still this paper technically is quite remarkable even now, 70 years later, right? But he does sort of allude to the fact that a localized system would not be able to thermalize and so on, right? So he somehow anticipated it, like, well, many other things in condensed matter, right? But really recent interest and recent progress is inspired by quantum simulation, right, and new sort of experimental ways of really probing these issues of thermalization or its absence, right? So it's an interesting history how this field went, and now going back to quantum simulation experiments, of course in quantum simulation, right, one natural experiment, as we discussed, is a quantum quench, right? So we can ask, so what does quantum quench in an MBL phase do? So what does it look like? How does evolution progress? Because in a thermalizing system, so we discussed, right, what happens. So you would thermalize, entanglement would spread, and your observables would fall to their Gibbs values, right, or microcanonical, whichever ensemble you prefer. So here, to understand dynamics in the MBL phase, it is convenient first to rewrite the Hamiltonian in terms of conserved quantities. And in this case, I can go back here and define operator basis using tau I x, tau I y, tau I z, and their products, right? And then, so since H commutes with all the tau z's, so it must be proportional to, it must be a superposition of only products of tau z's, right? So it must be that I have some Hi tilde tau Iz, right? Jij tau Iz tau Jz. Then I'm allowed to have, less local terms, right? Ji, Jk tau Iz tau Jz tau Kz. But since it came also, so I obtained it by doing a quasi-local unitary transformation of an original local Hamiltonian. So this would be a quasi-local Hamiltonian also, right? Which would tell me that these interactions have maybe exponential tails, right? But they are exponential tails. They decay quickly. So, and that means, for example, that if I were to look at effective field experienced by spin number I, right, Hi effective, it depends on the configuration of other tau z's, tau I, with I not equal to my spin, right? So other spins, I can view it like that other spins create Z field for my spin. So I have plus some Jij tau J Z with J not equal to I capital. Then I also have, 3 spin terms and so on, right? But natural expectation is that contribution to this field from spins far away would be exponentially suppressed in the distance, right? So all of these coefficients, jij, jijk, would all decay exponentially in terms of separation between the spins. And once we have this representation, dynamics becomes very simple, right? It just tells me that in this basis, what the spins do is just dephasing, right? Because eigenstates pick up different phases, right? And there are no transitions to worry about. And so if I'm thinking about the quantum quench starting from a product state, so let's say psi0 is a product state in the physical basis, that would be, for example, let me consider a state where each spin is prepared in the eigenstate of X, sigma X Pauli matrix, right? So for me, plus would be up square root 2. These are physical spins, but let's say if I'm deeply in the perturbative regime, I can think of this type of superposition of the tau spins, right? So I could say that this is, of course, up to corrections. This is approximately my conserved spins. Over square root 2. And then what I have, right, in terms of dynamics, is I have my tau spins, which are originally sitting in the xy plane along x direction, right? But under this Hamiltonian, they would dephase, they would get entangled actually, right? And that's curious. So these spins would pick up phases, these states would pick up phases depending on the state of other spins. And this would lead to entanglement, right? Entanglement between spins I and j with distance x apart. So the phase of this it would get dephased by spin j after time which is approximately inverse, right? Inverse of their interaction, right? After time of x, which is 1 over j ij, but j ij decays as e to the minus x over kappa, right? So there are these remnant interactions which are very weak, but nevertheless, in a generic quantum quench experiment, they would generate very slowly entanglement, right? And then I would say that the spreading of correlations, just inverting this formula, so x of t goes as some constant times log of t. Right, so this predicts that entanglement would spread in a quantum quench, but would do so very slowly. So instead of fast, typically linear spread of entanglement in a thermalizing system, so here you have a very slow log growth of entanglement, which is non-universal in the sense that you see that here a lot depends on your initial state, right? So the overall prefactor would depend on the initial state. And then in the thermalizing system, you have a much faster, typically linear spread of entanglement, right? But this logarithmic growth can go on for many decades, and that's a hallmark of MBL phase, which, for example, distinguishes it from the Anderson insulator, right, where entanglement would not grow but quickly saturate at an area law. Right, so effectively, if you think about what this dephasing does, right, so it brings you to the diagonal ensemble with given values of tau z operators. So you could view it as a GG in a way, right, at long times, right? But it's a very peculiar GG because your integrals of motion are so local, right? So you, at long times, right, you evolve to diagonal, right, diagonal ensemble. And another curious implication of that is that your physical observables would actually equilibrate and they would reach some steady state values, but these steady state values would be very, very much non-thermal, right? So you have equilibration to a non-thermal state. With memory, right? With memory of of initial state of psi 0. And this memory arises because, right, because you have so many conserved quantities such that tau iz of time is a constant. But of course, you lose other information. So for example, that you had, whether you had, combination alpha up plus beta down, so you just retain the z, right, the z expectation value. There are other curious implications, so in particular that you can use the fact that here spreading of entanglement is related to dephasing, right? You only pick up z phases, but you don't change weights, and therefore you can play tricks like spin echo, for example, to recover at least partially your initial state. So let me not go there. And yeah, any questions? Vincenzo, Yeah. Well, it's non-universal and it has to do with your initial state, right? So I think, to me, that really depends, because if you manage to prepare a state which is eigenstate of tau z's, right, it goes to 0. So in a way, it has to do with the participation ratio of your initial state in the right, in the eigenstate basis. Yeah. So people, including ourselves, so we studied it for different examples. So you can see clearly that depending on the initial state, you get, right, right. Yeah. Okay. Any other questions? Okay, so then maybe let me make one more comment about MBL phase, and then we conclude. And right? And that's a comment about matrix elements. Right? Because we already can appreciate that MBL eigenstates are very different, right? Very different from thermal eigenstates. And as we said in the beginning, so we need to understand properties of the eigenstates and properties of matrix elements also. And let us, for example, look at what our expectation would be for some physical simple operator like sigma iz. And to understand that, so let me rewrite sigma z operator in the tau basis. So let me say that this is actually u dagger tau iz u. But now I will keep it in tau coordinates. So I can rewrite it as a sum of terms of range k, right? So this would be quasi-local. So I would have, and OK would be a sum of terms of range k. And I can, right? So I would have a general expansion. So O would look like something like that. So would be, some first constant ci z tau iz. Then I'll have terms which act on pairs of neighboring spins, right? So for example, I would have ci I plus 1, zz, tau iz, tau I plus 1z, right? Plus this types of coefficients, tau x, maybe tau y, right? This would be O2. And then I have, I'll have 3 spin terms and so on. And this would be quasi-local, right? So the weights of operator of range k would decay exponentially with some length scale, which let me, to keep it distinct from what we had here, let me call it another length scale. Maybe I'll call it kappa prime, right? But still, so I expect this to be quasi-local. And then you see that, we expect that there would be this tau z terms acting on one or a couple of spins, which of course, so their expectation value, so now if I look at the diagonal matrix element of that would be determined by tau z part, and that part would jump a lot, right? Because two neighboring eigenstates can have different values of tau z. So if I were to plot, or mm as a function of my eigenstate energy em, so I would see something that is all over the place, right? So it's very much non-ETH, and this has to do with, with all these conservation laws, right? So ETH in this case breaks down, and then another part, right? Another part, useful piece of information is what off-diagonal matrix elements do. And for example, to find matrix element of sigma iz between two generic eigenstates n and m, right, which come with some choice of integrals of motion. So generally, I would have to invoke some very long operator of range of the size of the system, right? But that means, because our operators are quasi-local, that this would be suppressed as at least like that, right? Probably more in practice, but at least it goes e to the minus system size over the scale kappa prime. Moreover, right, you expect that effectively the way the smallness arises, because to make transition between two eigenstates with a local operator, you have to go to a higher order of perturbation theory. So you expect this to be, first of all, very small, right? Much smaller than the level spacing. but also to be distributed according to log normal distribution. Right, so once again, you see that structure of matrix elements is very different. And right, and there is also, you can go back to our argument with, response of your system to tweak of the Hamiltonian. So what happens if I add a small perturbation to the Hamiltonian? So here you expect that a small local change of the Hamiltonian does not affect things far away, right? So this local perturbation should not induce a lot of resonances. And of course, this result is consistent with that, provided, kappa prime is sufficiently small. So it should be smaller than log of 2 or something like that, or 1 over log of 2. Right, such that this becomes much smaller than the typical level spacing, which is 2 to the power minus L. So, and that sort of closes the loop, right? So we gained a relatively complete understanding of phenomenology of many-body localized phase. As I said, and some of you already asked, of course, there is a question of exactly for which values of disorder do you see this phenomenology, whether there is some, very many spin, very slow resonance, which would destroy this as you go to extremely large systems and extremely long times, right? But, we know that this picture holds, right, that this phenomenology holds in a pretty broad range of disorders, right? And okay, it's been observed experimentally in several experiments with cold atoms and spreading qubits, right? So it is relevant to experiments. So okay, I guess you must be overloaded. These 4 hours of lectures are pretty exhausting, but so if you have any questions, so let's maybe stop here with this part of MBL. We will come back to it briefly tomorrow. And so tomorrow we will discuss a little bit, some other effects in between many-body localization and thermalization, right? In particular, this question of rare resonances. And we'll also discuss some other scenarios for non-thermalizing behavior. So pre-thermalization a bit and quantum many-body scars. But in the meantime, I think we still have time for some questions.
So in this perturbative construction of the MBLI case, you had this diagonal Hamiltonian and then the hopping perturbation. But the, let's say, interaction in the fermion language is like a ZZ thing in the diagonal. So what changes if we turn off that interaction?
Excellent question. So you find that the processes that you can have, right, are very restricted, right? Because effectively you're staying within this quadratic algebra, right? So whatever you do, ultimately it's immediately reduced to, right, to a single particle problem. Yeah. So it's just there are a lot fewer moves you can make, right? That's the usual sort of why are single particle problems or non-interacting problems are so much easier than interacting ones, right? Because you can, right, a lot of quantities you can essentially reduce to just evaluating single particle, right? So Gaussian states stay Gaussian states. Yeah, that's a good question. All right, I guess lunchtime.